thought of trees only as a particular kind of graph. However, it is often useful to add additional structure to trees to help solve problems. Data is often structured like a tree. For example, you can think of college life as a tree diagram. Take a look. Suppose we have some vertex here in our graph. This is going to be a rooted tree. And we have here a university, an arbitrary university, ABC University. So you start with a root, which we can consider to be your college or whatever. Then the college itself has multiple schools, like the School of Engineering and the School of Education and so forth. And then these can be thought of as children of the college, of the university. And so we call each of these neighbors of the root here children. But I want to specify that we can't just call them children because this tree is going to get very large in a moment here. These are specifically the children of the root. So that's how they relate to the root. It's important to understand that most of these relationships that we label are going to be related to the root and not necessarily always their parents. But we'll get to that in a moment. So likewise, you can consider each school to be siblings to each other. These children of the root can be broken down even further though. Each school will typically contain multiple degree programs. So for example, the School of Engineering might have mechanical engineering and aerospace engineering and so forth. Each degree program can be considered a child of their school. So these are also children, and I'll label these as degree programs. And again, so they're the children of the schools, but they're grandchildren relative to the root. And so that's how we label these things. Now, of course, degree programs are not actually grandchildren because this is just terminology we use for graph theory purposes. But again, we do call them grandchildren relative to the root when we're talking about this object, this structure as a rooted tree. So within each degree program are courses, and I'll only do one here. You can think of the rest as having branches as well. And I should say children. So these are courses. Within each course are topics that are covered and so forth. And so you can think of the topics are children of the courses. The courses are parents of the topics. Degree programs are grandparents of the topics and so forth. That's the terminology we use with rooted trees. All right, so there are many applications to understanding rooted trees. Hey everyone, real quick, I just want to mention that this video is a part of a whole course that I made. You can find a link to this entire course in the description below and make sure to click on that subscribe button. Let's do an example together. Consider the tree below, and we have here some labeled vertices, A through I want to say. If we designate vertex F as the root, which by the way is right here, there we go, that's F, then E, H, and I are the children of F because they're the neighbors of F. And so they are siblings of each other. Among the other things, we can say that A is a child of C. So that is a child of C because if we look at the structure of this tree, there's only one unique path from, excuse me, I drew that wrong. There we go. There's only one unique path from A to F. And so you can consider A as like the great-grandchild of F because the distance from F is 1, 2, 3. So the vertex G, we would say, is a descendant of F. That's another way we can say that. In fact, it's a grandchild of F. Vertices G and D, here, these two, are siblings since they have the common parent E. Now, why is E obviously the parent? Well, again, everything is established relative to the root F. And so E is closer to F and has neighbors D and G. And so D and G are children of E. E is a child of F, and so forth. The further you are away from F determines how you relate to each other vertex. Notice how this changes if we pick a different vertex for the root. If A is the root, then its lone child is C. So A is the root, C is the only child of the root. So C has only one child as well, namely E. We would then have, so this, by the way, let me label this as grandchild. We have F, B, G, and D, which are all the children of E. Notice how they're all neighbors of E. Now C is not the child of E, and that's really important because C is the parent of E, and so forth. So I want you to notice that we have F as a child of E instead of the other way around. Earlier, E was a child of F, but now F is a child of E. And F is the descendant of A instead of the ancestor. F and G are now siblings, where earlier G was the grandchild of F. And so the entire structure of the tree is completely determined by picking your root. And any of these vertices can be labeled as the root to construct the rooted tree that you want to construct. Anyways, thanks everyone, and I'll see you in the next lecture.